The title of today's talk is comparison between the multilayered perceptrons and the radial basis function networks, which we have discussed over the past few classes. Now, this comparison aspect is not going to take much of our time, but I mean, we need to discuss some of the things pertaining to our last discussion only, because towards the end of the last class we were discussing about the generalized solution to the regularization problem, okay, where in fact we had presented that in case that we choose the number of RBFs, okay, to be M1 instead of choosing it to be equal to n, okay, or the number of Green's function or the number of RBFs we choose to be less than that of n. In that case, I mean, basically the G matrix that evolves is not a symmetric matrix, and the G in fact becomes a rectangular matrix of size M1 by n, and we had to obtain the solution of the W's, okay, in terms of pseudo inverse of that G matrix, right. So, this is what we discussed in the last class, and in fact one thing which you have noted in our last class's discussions is that the argument that we are choosing for the Green's function, that argument is always the Euclidean norm of the argument. That is what we have been taking, and the Euclidean norm we are defining as the Euclidean norm of the vector, I mean vector difference between the input and the center. So, if Ti vector happens to be the center of the Green's function, okay, and if x vector is the input vector that we are feeding, so in that case the norm of the Euclidean norm of x vector minus Ti, where Ti is the ith center to it, okay, Ti vector is the ith center to it, and the squared norm of this, okay, I mean that is the squared Euclidean norm of this we were considering as an argument to the Green's function, okay. Now, just we deviate slightly, okay, in order to tell you that it is not that the squared norm, the Euclidean squared norm is always the thing that we are looking for, okay. Euclidean norm is okay, but we often find that the elements of this x vector, okay, that is x is actually composed of m0 number of elements that we know, and these m0 elements may, I mean, belong to different patterns, may belong to the to a different class. And in such kind of cases, what we need to do is sometimes we are required to modify the Euclidean norm, okay, and what we obtain after the modification of the Euclidean norm, we call it as a weighted norm, okay. So, we can express the Green's function, instead of writing the argument as an Euclidean norm, we can write the Euclidean, I mean Green's function's argument in the form of such weighted norms. So, let us now see that what kind of weighted norm are we looking for. So, we first have some discussions on the weighted norm, okay. Now, what we define as a weighted norm is that we define, I mean x is the vector that we are considering, and the weighted norm, I mean the weighted squared norm of the vector x, okay. This is also a squared norm, okay, different from Euclidean, I mean weighted, I mean, and weighted by what? Here we are making use of a matrix, okay, which is of size m0 by m0. So, our x vector is of dimension m0, that we know. So, x vector is of dimension m0. So, we choose a matrix C of dimension m0 by m0. Okay, so, C is going to be a matrix which we will be using in the weighted norm expression, and what we do is that we use this matrix, okay, as a weighting matrix. So, we will be calling this as the weighting matrix, and using this weighting matrix, the weighted squared norm could be expressed as Cx transpose Cx, this thing transpose times Cx. Okay. Very similar to the Euclidean norm, because in Euclidean norm, the normal Euclidean norm, what we do, Euclidean norm of x becomes, we know, equal to x transpose x. So, here what we are getting is that instead of x transpose x, we are getting Cx transpose Cx. So, it is only that x is modified by application of this C. Dimensionally it remains the same, because x is of dimension m0 and C is of dimension m0 by m0. So, Cx becomes of dimension, Cx also becomes a vector of dimension m0 only. Okay. And this is m0 vectors transpose multiplied by m0 vector. So, in a sense that this again gives us a scalar quantity for this one. So, which is in fact we are talking as the weighted norm. In fact, you can look at it, the application of this C. So, C is a matrix that modifies x. Okay. Very similar to the situation what we get when we take the affine transformations of points in the Euclidean space. What we mean by affine transformation? That supposing in the Euclidean space, say we have got a point. Okay. Let us say we have got one point which has got, okay, a 2 element vector. So, x1 x2, okay, this is the coordinate of that point, where x1 is this direction and x2 is this direction. So, x1 x2 forms a vector, and now if we rotate the axis, okay, by an angle theta, or if we scale, any application of translation of the axis, translation, rotation or scaling, okay, that together we call as the application of an affine transformation matrix. So, in effect what you do is that by applying the affine transformation matrix, you are transforming the point x into another transformed point, the affine transformed point. And here you are doing a very similar thing, that from the x space you are going into a Cx space, which is essentially some kind of a weighted space that it belongs to, and the resulting norm that we get is the weighted norm. So, using the weighted norm, actually the generalized form of the equation that we had obtained in the last class, that gets modified. So, you remember that we had obtained last time that f star x, and why are we calling it as f star? Because f star is different from that of f, because f is the exact solution, f is the actual solution for which we actually require n number of Green's function, okay, where n is the number of patterns, and each of those Green's function has to be will be having as its center the individual patterns that we are feeding. But as we are saying that instead of having n number of centers, we will be restricting ourselves to m1 number of centers. Okay. And so, having m1 number of centers, okay, our solution becomes approximate. So, that is why we are writing f star, not as f. And last time what we had obtained is that f star of x was written as summation I is equal to 1 to m1 wi g, whose argument was the Euclidean norm of x vector minus ti vector. Okay. Now, instead of writing the Euclidean norm, in this case what we are going to see is that we will write it with the suffix c, just like the way we did it here. That means to say that instead of taking Euclidean norm, we are taking the weighted norm. So, here the argument of the g function will be written in terms of the weighted norm, where actually taking the case of Gaussian function, using Gaussian as a Green's function, we can write. So, I think we write down here that for the case of Gaussian, Okay. We can write g of x vector minus ti vector, okay, taking it in the sense C, that is taking the weighted norm of x vector minus ti vector, that will be expressed as what? That will be simply expressed as minus x vector minus ti vector into C. I mean in fact one thing which I should have done over here is that I should have broken up this expression, this weighted norm expression. I mean if you simply break it up, then what it becomes? It becomes x transpose C matrix, and here it becomes, I mean C transpose, x vector C transpose, because here the whole thing has been taken as transpose. So, it is x vector C transpose C matrix x vector, okay, x transpose C x. This is what we are getting. So, in a very similar way, I mean since we are breaking up the weighted norm, okay, which exists in the argument of the Gaussian function, what we will be getting as the argument of the Gaussian function or within the exponential term, what we will be getting is x minus ti this transpose, then C transpose, because instead of x as we had used over here, here we are getting x minus ti, where ti is the center of the Gaussian function. So, this is x minus ti transpose C transpose, and then what? Tell me, do not keep quiet. C and then x minus ti, that is correct. So, x minus ti. So, this becomes the argument of the exponential, and in fact, we can write down this entire thing as I mean by some representation we can write it as minus half x minus ti, okay, transpose, and we are introducing a new matrix which we are calling as the capital sigma matrix. Okay. So, this is a matrix, okay, and we are taking the inverse of sigma matrix. So, I will be defining what this means, and this term. So, this term remains as this, and this term, that is x minus ti vector, also remains as it is. Okay. In between, what we have done is that instead of writing it as C transpose C, we are writing it as half of sigma inverse, okay, where actually the significance of this sigma is that it is the covariance matrix. So, where in this case the inverse matrix that we obtain, okay, the inverse matrix sigma inverse, okay, is defined by, it is just the weighting. So, it is half sigma inverse, okay, what we have written out here, that is a substitution for C transpose C, what we had in the earlier step. So, and in this case sigma, okay, the original sigma matrix is the covariance matrix. Okay. Now, all right, we will be, I mean there is nothing new that we talked of. I mean we are continuing the same old discussion of the last class only. Only thing is that I mean our idea was to show that yes, Euclidean norm is not always the restriction which you have to follow. The argument of the Green's function could be a weighted norm, and in terms of the weighted norm, okay, things can be expressed, like for the case of Gaussian, we could be expressing the weighted norm form like this, where this could be expressed in terms of sigma inverse, where sigma inverse is C transpose C and sigma happens to be the covariance matrix. Anyway, we will be, I mean the reason why I introduced this point is because we will be needing this thing shortly, okay, because the next topic which I am going to discuss is some amount of comparison between the multi-layered perceptron and the radial basis function networks. Now, we know that both radial basis function as well as multi-layered perceptron, they are essentially feed forward network. They are multi-layered feed forward network. Okay. One we are calling as MLP, multi-layered perceptron, okay, where we know that it is having a definite structure. I mean where we know that instead of I mean we are not restricted to one hidden layer, we could be having multiple hidden layers, but the neurons there look very similar, okay, whereas we are having the radial basis function networks where we are restricting ourselves to only one hidden layer, but the beauty there is that the hidden layers composition, okay, looks remarkably different from those of the neurons which are existing in the output layer, because the neurons in the output layer of an RBF network, okay, looks, I mean, as good as our old neurons, I mean, where we were simply linearly adding those things up, linearly adding the responses up. So, in output we did not have anything revolutionary concept, whereas in the hidden layer activations, the hidden layer activations were remarkably different from the kind of activations that we had used in the case of multilayer perceptrons. Because for the case of multilayer perceptrons, what we had used was that the activation was essentially based upon the dot product between the weight matrix, I mean the weight vector and the input vector. So, we were having W transpose X, okay, which was deciding our activation. In this case, what decides our activation is X vector minus Ti vector, Ti being the center of the function. Okay. So, I mean the computational mode is remarkably different. Okay. But one thing can be said always, okay, that if for solving a problem you have got some problem to solve, and there you have decided to use a multilayer perceptron following the back propagation model. Now, I mean whatever the multilayer perceptron can do, the same mimicking can be done using the radial basis function network also, and it is vice versa. That means to say that if somebody is using a radial basis function network to solve a problem, okay, the same problem can be mimicked using a multilayer perceptron. Okay. So, this mimicking ability is there. That means to say that they have got a good deal of similarity, okay, in their structures and everything. It looks quite similar. Both are essentially nonlinear mapping, okay, because we are, I mean, even the multilayer perceptron starting point was also that we have patterns, okay, which are non-linearly separable in the input space, and we could realize that, okay, using the hidden layer, where in the hidden layer we had separated out the different linearly partitionable spaces and then added them together in the subsequent output layers. Whereas, in this case what we are doing is that we have just taken a different approach and we took and we looked upon the whole problem as a function approximation problem, or to say in a more modest way, the surface fitting problem. Okay. So, coming to the comparison of the radial basis function network and the multilayer perceptron, okay, there are some points that can come to our mind. Number one is that when you talk of RBF, okay, I think we can list out the comparisons like this. We have RBF this side and MLP this side. RBF is having single hidden layer, okay. I mean that is in its very basic form, okay. Not that people haven't experimented with multi-layered RBF, but really speaking, multi-layered RBF doesn't serve much of a purpose, because this sort of a mapping is possible. I mean it is possible to realize this mapping using single layer only. I mean only thing is that yes, you decide that how many number of RBFs you use as the hidden layer, okay, and what you choose as the centers. Those are some of the very crucial decisions, okay. But in its basic form, single hidden layer is good enough, whereas MLP can have, it may have more than one hidden layer. Then the second point is that the RBF has got hidden layer computation nodes different from that of its output nodes. So, hidden layer computation nodes, hidden layer computational nodes are different from output computational nodes. That is very much obvious, because in hidden layer we are using the RBF activation functions, whereas in the outputs we are using the linear activations. And in the case of multilayered perceptrons, okay, we are using, I mean, it follows a common computational model. So, it follows common computation model in hidden as well as output. Okay. The third point about the comparison is that in the case of RBF, the hidden layer is nonlinear. Okay. And output is what? Linear. Output is linear. We had seen that, because whatever nonlinear mapping had to be done, that was done in the RBF layer itself. I mean, in the hidden layer itself, we did the nonlinear mapping. Okay. And then once the nonlinear mapping has been carried out, the rest could be linear. Whereas in the case of multilayer perceptron, what happens? I mean, hidden is nonlinear, output also nonlinear. We are using the sigmoidal activation functions typically. So, hidden and output, okay, both are nonlinear. Okay. Although in the regression, in the nonlinear regression, so this is actually true when we are using the MLP as pattern classifier. As pattern classifier, we will be using both hidden layer and output layer as nonlinear, whereas for the case of nonlinear regressions, okay, because you know MLP can be used for pattern classification problems, where the purpose is to just divide the patterns into a number of known classes, okay. And the other way of looking at it is that where we solve a regression analysis problem, I mean more of a generalization problem, where we can use the output layer, I mean there the output layer could be linear, okay, in the case of nonlinear regression. Okay. So, these are up to the third point. So, these 3 points are quite obvious, and now the fourth point says that the, I mean about the argument of the functions, okay, which we have already talked of. Okay. The argument of the, so here RBF and here MLP, the argument of the activation, the argument of the activation function of the RBF activation functions computes the Euclidean norm or weighted norm, whatever, okay, between input vector and the center, whereas in the case of multilayered perceptron, okay, each hidden unit computes the inner product, each hidden unit computes the inner product of what? Input vector and synaptic weights. Okay. The last point is that in RBF, can we call it as a local or is it a global function? It is definitely a local function, because we had seen that we are employing the centers for those RBFs, okay, and definitely the response, okay, depends upon those centers, and as you go away from the center, the response decreases. So, it is actually an exponentially decaying local characteristics. Whereas, in the case of multi-layered perceptron, it is doing global approximation to nonlinear input output mapping. All right. So, I think these points are pretty obvious. In fact, here, I mean, one can always say that structurally, I mean, although capability wise both RBF and MLP, okay, can do the same thing, that is to say, solving non-linearly separable problems, both RBF and MLPs are capable of doing that. RBF looks little complicated in the sense that, okay, the type of functions that it is using, okay, is not as simple as the kind of functions that were used in the multilayer perceptron, because the computation of the sigmoidal functions are pretty simple. Okay, in fact, hardware units are also available nowadays where the sigmoidal activations can be computed in hardware itself. Okay. So, that way computationally, yes, computing so many different RBF functions is could be the only involved thing, but otherwise structurally RBF looks pretty simple. And in fact, one of the points which we should note at this stage is that coming to the training of the network, in the case of multi-layered perceptron, we had seen that the training is quite involved in the sense that we are feeding the inputs, all right, and then we are getting the outputs, the actual outputs different from that of the desired outputs, and then the error that we are having, that error is in turn guiding us to adjust the synaptic weights, okay, from the output layer back up to the input layer. Okay. So, we proceed from the back to the front, okay, and using a back propagation of the error, we were making it learn. So, we had to adjust so many different synaptic weights. But coming to the training, if one asks us about the training of an RBF, well, where is the training involved? Okay, as far as the synaptic weights are concerned, okay, the only place where we are having synaptic weights is where we are combining the RBF outputs into the output. Okay. All the RBF outputs are taken together and then we are deciding upon an output, and there only we are having synaptic weights. So, learning is only that much, that is what we may think. Are we right in saying that only those are the synaptic weights? But coming to the point that is it the only learning that is involved in the RBF? What is the answer? Yes or no? Do you think that only learning the weights of those the weights of the output to the the RBF output to the actual output, okay, only learning those weights are enough for a learning mechanism in RBF? Okay, well, many people said that the answer is no, and why? Let me invite that discussion also, that why do you think that there are some more learnings that is involved? For each node the radial basis function varies, but one thing that we are choosing a particular type of a radial basis functions, let us say Gaussian. So, once we choose Gaussian, then all the nodes are at least having Gaussian functions, okay, the centers are varying. Now, the kind of discussions which we had so far, there we have been telling that as if to say that we have decided a priori that there are m1 number of different radial basis functions existing, and we are feeding the input vector, and the input vector will be going to those RBF computational nodes, okay, which will be computing the Euclidean norm and then finding out the responses of all these different RBFs. Okay. So, as if to say that a fixed structure of RBFs if we choose, then actually speaking there is no learning that is involved. But if I ask you one thing, that who says that my choice of centers are the best? You see, as long as the problem is that I am having n number of different patterns and I choose n different centers, each center corresponding to the patterns which are actually existing in our training space, well and fine, it is understood that we have used the training patterns themselves as the pattern centers, and we have n such training patterns, we constituted n such centers. But the question comes that when we are saying that n, the number of patterns, is too large a number to construct a radial basis function network, and we have decided to reduce the dimensionality from n to m1, okay, then the immediate next question is that how would you choose this m1 out of n? Okay. And even if you happen to choose m1 out of n, some arbitrary way, some random way, okay, where is the guarantee that this is the best type of an arrangement? Or could there be some adaptability that depending upon the patterns which are actually existing in the input space, okay, we may be prepared ourselves to adaptively adjust the centers from one iteration to the other. If we can adaptively adjust the centers of those radial basis functions, in that case you see we are bringing in another degree of learning mechanism in the radial basis function network. It learns what? It learns the positions of those centers. We can start with some arbitrary positions of the radial basis function centers, all right, make that network learn, and then we can adaptively adjust the positions of the centers in accordance with whatever input vector that we are actually feeding to the system. So, if we do like that, then the learning in the RBF is to be looked upon as a two-step strategy. Number one is the learning that we incorporate in the RBF functions itself, choosing the centers of the functions where the first degree of learning is involved, and only when this learning is over, okay, then we can afford to go in for the second level of learning, which is the learning of the synaptic weights from the hidden layer to the output layer. Okay. So, learning is to be looked upon as a two-step strategy in the case of RBF. So, I thought that before we introduce the next topic in our program, that is the principal component analysis, which I said in fact in the last class that I will be introducing that, but I thought that maybe some discussions are very much needed to give you a treatment of the learning mechanisms in the RBF. So, that is what I intend to cover in the remaining part of today's lecture. So, let me tell you about, I mean, in terms of the learning strategies in RBF. Okay. We can list out several learning strategies. The first one is where we have fixed centers selected at random. So, we can choose the centers okay, randomly. I mean, if we adopt this strategy, fixed centers selected at random. So, there what we do is that we choose the function g of, as argument we take x minus ti vector, okay, this squared, okay, can be expressed as, I mean, if we happen to choose the Gaussian as the radial basis function, in that case the argument of this exponential will be minus sigma square, that is what I mean, minus 1 upon sigma square times, we can have this, that it will be 1 upon sigma square or 1 upon 2 sigma square, that is right, yeah, 1 upon 2 sigma square into norm of x minus ti square. Is it correct? So, where sigma happens to be the standard deviation of the Gaussian function, and in fact, so this is the standard deviation, and how many such TIs are we choosing? Let us say that we are choosing M1 such centers. Okay. So, we choose I is equal to 1, 2 up to M1, right. So, what we do is that we have to determine the standard deviation. This is very important, because what happens is that if we choose the standard deviation to be too small, that means to what? That means to say what? We are choosing very narrow Gaussian functions, and very narrow Gaussian functions will be having a disadvantage that it will be, I mean, highly local in nature. Highly local in nature means its response will be only centered around that, okay, and as we deviate from the center, the response of that will be very poor. So, there will be a number of patterns, okay, which will not be getting any response. I mean, if we consider the total input space, then in the input space there can be existence of a number of patterns which will be having small response. So, that is why sigma should not be too small. Again, the problem of sigma choice as very large, sigma, if we choose sigma to be very large, in that case we are avoiding that problem, no doubt. But then we are inviting another problem, that large sigma means what? That we we are not choosing this TI alone, we are choosing M1 such TIs. So, there will be M1 such different centers, and the responses of those RBFs will be overlapping with each other. Okay. So, there are two things in it. So, that is why this sigma is to be very judiciously chosen. In fact, one of the norms which people have followed in choosing this sigma is that they decided to choose sigma as d max by root over 2 m1, okay, where d max happens to be the maximum distance between the chosen centers, where d max is the maximum distance between the chosen centers. So, if we do that, I mean, if we apply this definition of sigma, okay, then the Gaussian function that we use can be expressed as g of norm x minus ti whole square is equal to exponential to the power minus m1 by d max square, okay, Euclidean norm of x minus ti square. Okay. M1 obviously is the total number of such centers that you are using. So, here what yeah. So, that means to say that we are choosing uniform sigmas. I mean, for all the centers, I mean, if we choose the sigmas like this, then for all the centers, okay, for all the Gaussian functions that we are using as RBFs, okay, we are having the same amount of standard deviations. Okay. So, that means to say that they are equally spaced. Okay. But one thing which one should note is that when we have a pattern space, I mean when in the input space we have got some training patterns, we may find that the patterns are very much clustered in some areas and the patterns are quite sparse in some other areas. It can happen. Okay. Patterns, I mean quite sparsely populated in some regions, I mean in the M0 dimensional space only. In some regions it is sparse, some region it is dense. But if we happen to choose the centers, fixed centers at fixed locations uniformly apart, in that case the disadvantage that we are getting is that there will be some centers which we are keeping unnecessarily, because within its region of activation, okay, there is not many patterns to expect from. Okay. So, their responses will be poor. So, I mean we are just wasting, as if to say, wasting those RBF nodes, okay, where the population is not dense near to its center. Okay. Whereas, in some regions we may be having large population of patterns, but there may be just one center, where we may find difficult to actually discriminate between the patterns, because I mean pattern classification is our main motto of using this RBF. So, where we will be unable to distinguish between the patterns, where the patterns are highly clustered and close. So, in fact, this itself suggests that instead of choosing fixed centers, okay, we should be allowed to play with the centers, okay, where if you find that somewhere the region of the concentration of the input patterns is more, shift more centers towards that. Try to design the RBF with having centers in those populated areas and having less number of RBFs in unpopulated or sparse areas. Okay. Something like that you can design. So, this itself suggests that there is a scope of adaptability in the space, I mean in the center allocation. In fact, one thing that leads to is that if we use fixed centers, okay, for example that we use fixed centers, assuming that the input patterns are uniformly distributed in the M0 dimensional space, okay, and we can afford to use fixed centers, then the only learning for fixed center case, the only learning that is involved is the adjustment of the synaptic weights. Okay. And synaptic weights also we know, because last time in the last class we had obtained a solution of the weight vector as what? Remember, we had obtained it as G plus, where G plus is the pseudo inverse of the G matrix, D vector, okay, where D vector is the desired response vector and G plus is the pseudo inverse of matrix G. And our matrix G's definition was that G was consisting of the elements G, J, I, okay, where in the case of Gaussian functions used as RBFs, G, J, I was expressed as exponential to the power minus m1 by d square, okay, norm of xj minus ti square of that. Okay. This was our Gi, where j varies from 1 to n, that is correct. Why n? Because n is the total number of input patterns. So, x's index is j, so it corresponds to how many patterns are we having. So, j can go up to n, and what is the index of I? That is very correct, 1 to M1, because there can be M1 number of centers. So, I is the index of the center and j is the index of the pattern, j varying from 1 to n and I varying from 1 to M1. Right. So, now the whole problem for us, I mean, in the computation of the synaptic weights is computation of this G inverse, or I mean computation of the pseudo inverse of G. Okay. In fact, pseudo inverse computation, I mean good techniques are available to compute G plus. In fact, very fast and efficient algorithms, computer algorithms are available whereby one can obtain the pseudo inverse of matrices. Okay. Now, just one very popular technique of that is by the method of singular value decomposition. Okay. Those who are having good background about matrix algebra may be already knowing that, but for the benefit of all, I mean let me give you some idea about this singular value decomposition. Actually, in the case of singular value decomposition, what we say is that G, our matrix G that we are taking is actually an n by m matrix. Is that correct? Because n is the number of patterns, m is the number of, yes, m is the the number of RBFs that we are using. So, it is n by m matrix. We were taking m1, that we are taking m, and for G, okay, there exists two orthogonal matrices. So, if G is a real, okay, if G is a real n by m matrix, then there exists, okay, two orthogonal matrices, okay, which we are defining as a U matrix. U matrix in fact is consisting of n number of vectors u1, u2 up to un. So, we have a matrix consisting of n number of vectors and another matrix V, okay, which is consisting of m number of vectors. So, this is V1, V2 up to Vm. In fact, to say that all these individual vectors u1, u2, all these vectors are of dimensionality m. So, U is actually an m by n matrix, whereas V, here there are m number of vectors defined over here, where each of this vector is of dimensionality n. So, V is actually of dimensionality n by m. Okay. So, this is to say m by n, whereas V is n by m. So, in fact, why are we saying this U matrix and V matrix to be orthogonal? Because we can, I mean, it is possible to find this U matrix and V matrix such that U transpose G V, okay, this actually diagonalizes this G, okay, by the pre-multiplication by U transpose and the post multiplication by V, okay, makes the diagonalization of G, and in fact the diagonals that results, okay, those diagonals are referred to as singular value. So, that is why by choice of this U matrix and V matrix, okay, what we are essentially obtaining is a singular value decomposition. So, this is to be diagonalized. So, we get a diagonal matrix, okay, whose elements, whose diagonal elements are sigma 1, sigma 2 up to sigma k, okay, where k is actually the minimum of m and n, okay. And here the diagonalization will be such that sigma 1 is greater than or equal to sigma 2 is greater than, I mean this will be ordered, okay, up to sigma k, and these should be greater than 0. In fact, all these sigmas are called as the singular values, and this kind of a technique we are referring to as the singular value decomposition, where we are decomposing this G into such kind of singular values. Now, if G can be decomposed into singular values by finding these two matrices U and V, then it is possible for us to get back the G pseudo inverse, the G plus matrix. Okay. In fact, we can obtain, okay, by applying a transformation like this. So, G plus matrix can be recovered as V sigma plus, okay, U transpose, okay, where sigma plus matrix, okay, is an n by n matrix, and sigma plus is actually defined as the diagonal of 1 by sigma 1, 1 by sigma 2 up to 1 by sigma k, and rest of the elements in that are zeros. So, if we can form, I mean, since we have through the singular value decompositions we have got sigma 1 to sigma k's, okay, we can now form a diagonal matrix with the elements of 1 upon sigma 1, 1 upon sigma 2 up to 1 upon sigma k, okay, and then I mean this will be the minimum, k is the minimum of n and m, whereas we have to go up to n. So, if it is m, then we have to fill up the rest of the elements with zeros. So, this becomes the sigma plus matrix, and making use of the sigma plus matrix, and because we know the V matrix and the UT, we can get the G inverse. So, this is the pseudo inverse computation. So, pseudo inverse computation, okay, good techniques are available. Now, so this is about the fixed center case, okay, where we find that the only learning that is involved is in the output layer, where we have to learn the synaptic weights. Okay. In fact, synaptic weights there is a direct solution, because if we are knowing G plus, in that case synaptic weights can be computed directly. In fact, there is no learning, that is no iterative kind of a learning which is involved over here. Okay. You simply compute G plus, okay, you already have the D and you compute the W straight away. Okay. But the next strategy is actually selection of self-organized centers, okay, where we are going to tell about some kind of a learning mechanism in the adjustment of the centers, that we will be talking in the next class. So, where the learning mechanism of RBF we will continue for some time before we introduce the next topic. Okay. Thank you very much.